Okay. Hi, everyone. Thanks so much for coming out. Really appreciate it. Those who are calling in, if you're not in Southern California, you missed a beautiful day. It was like in the low 80s. I'm in shorts right now. So I grew up in Tennessee. I went to school in Philadelphia and Arizona. So yeah, Southern California has great weather. So I'm Rob. I work at JPL. I'm here to talk about exoplanets or finding life in the galaxy because I'm a giant nerd. I love Star Wars. I want to ride the Millennium Falcon one day, but in order to do so, I have to know where it's docked, right? So that's what I'm trying to find is the next place I can ride in the Falcon. So as I mentioned before, I'm from JPL, just down the road, down the hill, however you want to get there. Obviously, this photo was taken thousands of years ago when Southern California had water on its in the mountains. My building is, for everyone else online, is this one right here. No windows, so it's really great. Let's see if I can do pointer options. Visible. There we go. All right. And I get lots of people asking me if I ever wanted to be an astronaut when I grew up as a little kid. So this is actually young Rob at Kennedy Space Center outside of Orlando, meeting his hero, the astronauts. And when people ask me if I ever wanted to be an astronaut as a kid, my answer is a hard no. And that's because I'm definitely afraid of heights. And that's kind of a job requirement to be an astronaut these days. So I'm the next best thing. I'm what I call myself an exoplanet astronomer. So let's unpack this. Exoplanet, this is just short for extrasolar planets. And extrasolar means anything beyond or outside of our own solar system. Planet, hopefully you all in an astronomy club know what that is. So we'll skip that. So an exoplanet, very inventively, astronomers have horrible naming schemes. It's any planet outside of our own solar system. And an astronomer, hopefully you all know what that is too, being in an astronomy club, someone who stares at the sky, or really in my case, my computer, for way too long. People always wonder if I'm always at telescopes. I'd love to be. I maybe only get up there maybe 5 or 10 times a year at best. But this laptop right here is my biggest, best tool. It's what I use all the time to do all of my work. So even doing observations now, it's pretty incredible the automation you can get on telescopes, and you can sign in easily to anywhere in the globe from, somewhere like in Southern California to Hawaii and be able to use those telescopes. So it's pretty awesome. Yeah. Actually, Mauna Kea, they had these big multiple buildings of dorms. And now today they're pretty empty because most people remote observe in Hawaii. Because even though we love going out to Hawaii, it's a little expensive to get out there. So at JPL as an exoplanet astronomer, I'm hoping to answer this big question: are we alone in the universe? And before we talk about aliens, which is why I know all of you came out tonight, not just because of Candy's awesome snacks, but also, that's what I want to do is help find, hopefully, alien life out there in the universe. Before I talk about that, though, I'm contractually obligated to give you some history lesson because my wife is a historian. So if I don't give this slide, she yells at me when I get home. So bear with me for a minute. So exoplanet science is actually one of the newest fields in astronomy. It's been around since roughly the mid-90s when the first exoplanet was ever discovered. So it's actually one of the youngest fields in all of astronomy. But despite that, the idea of exoplanets, planets outside of our solar system, life potentially existing on these other bodies, the idea has been around for a while. So for example, Giordano Bruno was a 16th century philosopher. He's that pewter-looking dude on the right, maybe like Emperor Palpatine, maybe, for the Star Wars fans out there. He actually postulated the existence of planets outside of our own solar system. And Isaac Newton, as you all know as the inventor of Fig Newtons, right? He said in his book Principia, where he actually discussed his theory of gravity, he said in the same book about it, he said, and if the fixed stars are the centers of similar systems, they will all be constructed to a similar design. In other words, here in our own solar system, we have 8 planets. 8 because Pluto is not a planet, right? No, it's not a planet. I'm sorry. We're starting off on that. Pluto's not a planet. So we have 8 planets around our own sun. So it stands to reason when you go in the night sky that when you see all those 2 stars from LA, and I've heard rumors of tens or hundreds more stars in the universe outside of LA, when you look at the night sky, you know that those stars also have planets around them as well. And now we know a few hundred years later, these 2 dead guys are absolutely correct. There are thousands of exoplanets. Yeah.
Quick slideshow on there so that the people online see slideshow?
You should be seeing slides, everyone online.
I see slides, but then all of the upcoming ones.
Oh, you're seeing presenter mode. Sorry. Let me share the other display. Let me share this one. Okay. Does that work?
Yeah.
Cool. Thank you. Appreciate it. No worries. As our technology gets better, and as we know where to look, when to look, how to look for exoplanets, we've been discovering more and more every single year. And since we started looking and discovering planets in the mid-90s to today, we now know that we've discovered at least over 5,000 exoplanets. And based on statistical arguments, astronomers today think there are many planets as there are stars in the sky. So there's hundreds of millions of stars. There's probably also hundreds of millions of planets as well in our own Milky Way galaxy. So exoplanets are everywhere. They're ubiquitous. There's a lot of them. So how do we find life? I've made this simple 3-step method you can follow for 1995. First off, you have to find an exoplanet. Then you have to determine if that planet could support life. Just because it could doesn't necessarily guarantee that it actually does have life on its surface. And then step number 3, you actually have to find that life if it does exist on the surface of that planet. So let's look at some various ways that we can use to discover exoplanets. But there's a big problem on this, and that's because it's very difficult to see planets, specifically exoplanets. They're so very far away that we typically only see the star they're orbiting. And that's just because the star is so much brighter than the planet. And the brightness of the star obscures any of the light from the planet as well. So we either need to block out the star, remove its light to see the planets orbiting around the star, or we can use other methods to infer that a planet is orbiting around that star instead. And there's actually a variety of different methods that we use today to discover exoplanets. But the 3 that I'll be focusing on tonight, the radial velocity, the transit, and the direct imaging methods. Radial velocity and the transit methods have arguably given us the most information that we know about exoplanets to date. And I'll also talk about the direct imaging mission because that's one of the projects I work on at JPL. So I like to keep my bosses happy. So let's look at the radial velocity method. So if we're looking at an exoplanet orbiting on a star, the star's gravitational tug will keep the planet in orbit around that star. But the planet is also inducing a gravitational tug on the star as well. So the planet actually causes the star to wobble back and forth. For about an Earth-sized planet around a sun-like star, I think it's about a centimeter a second. So like a nice walk. And this method is called the radial velocity method. What we're able to do is we can actually look at the spectra of the host star and watch the spectral lines of the star Doppler shift back and forth. So as the light of the star comes towards us, as the star wobbles towards us, the light of the star will become blue shifted. And then as the star wobbles away from us, the light becomes red shifted. So you're all probably familiar with red shifting of light and blue shifting of light. It's very much akin to if you're walking on the road and a very obnoxious loud car passes by or an ambulance passes by, it'll increase in pitch. The sound of it will, because the sound waves are being compressed. But when the ambulance or obnoxious car drives away from you, those sound waves are stretched out and the pitch becomes lower. Same exact thing happens with light. When the light is coming towards us, the wavefronts compress slightly, and that causes an increase in frequency, blue shift. And then when the light of the star comes away from us, the wavelengths of light are stretched out a little bit, and it's red shifted. So we can actually look at the Doppler shift of the star, watch it wobble back and forth, and from that we can infer that there's a planet orbiting around that star. But this method is also extremely powerful because this gives us the mass of the planet as well. The bigger the planet, the more wobble it induces on its host star. So you can actually directly weigh these planets just by using their Doppler shift, which is pretty incredible.
I have a question.
Yeah.
Multiple planets.
So we have a question from the audience about multiple planets.
Now,
Yes.
What sort of effect does that have on?
So the question is for folks online is what does the effect of multiple planets have on the radial velocity signal of this? So as we play this animation, you'll see in a second the light waves kind of look like a sine wave. So that's a sine wave going back and forth, and that's wobbling the star back and forth. And if we add an additional target to that system, you'll see more sine waves sort of superimposed on each other. So it'll be sine waves on top of sine waves, basically. And if you get tons of planets, it's a giant mess and hard to decompose for sure. Right. So the other way we find exoplanets is using a method called the transit method. And this one's really near and dear to my heart because this is what I specialized in grad school. So bear with me for a minute. Sorry. So if we're observing a star, if we're really lucky, that star will have a planet orbiting around it. And if we're even luckier, that planet will pass in between us and its host star. And then relative to our line of sight, that planet will block out some of the star's light. And the amount of light that that planet blocks out tells us directly how big the planet is. The more light that's blocked out, the bigger the planet. The less light, the smaller the planet. So this is the transit method. And this is extremely powerful because this allows us to measure the radius of the planet relative to its host star. And as I'll talk a little bit later about as well, the transit method also enables us to study the planets, the atmospheres of these planets as well. And instruments like James Webb, like the Hubble Space Telescope, they're currently using the transit method to characterize the atmospheres of these targets. And the transit method has been used very successfully to discover exoplanets as well. It's been already discovered 4,000 of the currently known 5,000 planets to date. And that's thanks to ground-based surveys. That's also thanks to missions like NASA's Kepler and TESS missions, which I'll talk about in a second. And those have enabled us to gain a ton of statistics on the existence of exoplanets as well. So for the transit methods, some advantages of this method is it's relatively cheap. I saw a post online a few years ago. Someone had a simple DSLR camera on a really simple barn door tracker. Just with a camera alone, they observed a transit. We have folks across the world using 4.5-inch telescopes to get really high precision transit measurements as well in our collaboration. And Ryan, I think you observed one from your driveway once, right? So you can even do it from this area too. So if you have questions on how to observe, bother Ryan. Again, the other advantage is it gives us the size of the planet. But some disadvantages is that we're biased towards large planets, as they're just easier to find. The bigger the planet, the bigger the signal. We can have false detections, and also we need that geometry. If a planet is orbiting perpendicular to our line of sight, the planet never passes in front of the star, a transit never occurs, and that shadow is never cast on the Earth. But despite that, thanks to missions like NASA's TESS mission, or the Transiting Exoplanet Survey satellite, this is doing a full sky survey of the entire sky to look at and discover more exoplanets. TESS is actually predicted to discover an extra 10,000 exoplanets. So again, today we know of 5,000. TESS is going to hopefully discover an extra 10,000 exoplanets.
This isn't up there yet?
This is up there right now.
It is?
Yep. It's been up there for about 4 years or so. And it's already discovered a few hundred exoplanets as well. So you might be wondering, Rob, you already have 5,000 exoplanets. What's an extra 10,000 other than bragging rights? And the answer is because we need as many good targets as we can to observe transits using large telescopes, either from the space or from the ground as well. So the Hubble Space Telescope, for example, that has observed about 50 to 60 transiting exoplanets and characterized the atmospheric composition of these planets. James Webb is predicted to look at tens, if not hundreds of planets. I've heard some estimates of about 200 targets that James Webb will be observing. Ariel, this is a mission that'll be launched by the European Space Agency, so Europe NASA basically. This mission will be launched by the end of this decade, roughly. So just in another, in a few more weeks, just 6 more years. So right on the corner. And Ariel's dedicated to observing exoplanets. And Ariel will observe up to 1,000 exoplanets. So we're building our foundation here and adding upon it and improving things and getting more and more data. Because up until this point, we've been very, very data starved in exoplanets. You kind of lived and died by the data access. And now when we get down to the Ariel age, we'll have a true statistical sample for the very first time ever, which is pretty exciting. And then beyond these 3 missions, likely next generations of missions they'll be launching in the 2030s and 2040s will still leverage the transit method to characterize the atmospheres of these planets. And again, I'll go over in a few minutes how we actually can characterize the atmospheres of these planets using the transit method. But in order to observe a transiting exoplanet with something like Hubble or James Webb or Ariel, we have to know exactly when that transit were to occur. So let's say, for example, I have a favorite exoplanet and I want to write a proposal for James Webb Space Telescope time. And I say, I need this window of observations to make sure I observe that transit event when the planet passes in front of the star. If there's any uncertainty of when that transit occurs, that's additional observational overhead I have to build into my observing program. Typically, it's not a big deal. It might be a few minutes. And, on a target by target basis, that's not a huge ask. But then when you start doing the math and you figure out how much 1 hour of James Webb time is worth, 1 hour of James Webb time is worth about $100,000 to $1 million. So you really want to use it as efficiently as possible to save all of you your taxes, right? And also, there's just a lot of people. Everyone wants to use in astronomy, everyone wants to use James Webb and Hubble. So we want to make sure we use it as effectively and efficiently as possible. So if there is an uncertainty in the transit event, 5, 10, 15 minutes, that's time we want to save from James Webb, and especially Ariel, because 5 minutes times 1,000 targets, that's suddenly a lot of time that's wasted waiting for these transits to occur. But luckily, this is where small ground-based telescopes can help out. So on the right is some actual transit data right here on the right-hand side of the screen. And this was taken actually by a single 6-inch observatory in Tucson, Arizona, out here in the US. And this shows you a typical transit event. Right here, observing the host star. Then here, the planet gets in the way of the star, causes the star to dim. And here, the planet gets back out of the way, so the star becomes brighter again. But this data was taken with that single 6-inch robotic telescope. And looking at this data quality, I was honestly blown away. I couldn't believe how great it looked from just a single robotic telescope with imperfect tracking. The target on here wandered across the focal plane by like 300 pixels. There's no flats, there's no darks, there's no biases, there's no calibrations at all. And yet, we're getting a beautiful data set that's saving us time. So that made us think, well, there's really, we have this big problem. We need to save time. Small telescopes can help us out because they can measure these mid-transit times of these targets, and we can help out James Webb and Hubble. But we have up to 1,000 planets to observe. What do? And this is where all of you can help us out, is we started a citizen science project called Exoplanet Watch. Because quite honestly, there's too many targets for us to observe with professional observatories. And not all of them are needing an 8-meter class telescope or even a 1-meter class telescope. Folks like Ryan can go in his driveway and set up his telescope, which is like 65 inches. How big is your telescope? 5 inches. There you go. So Ryan has a perfectly sized telescope. And with your 5-inch telescope, Ryan can hit on about 200 targets, at least, with this setup, even out here from La Cañada, La Crescenta area. So we actually had a student that observed a target with a 6-inch telescope right off the shelf, and he observed it from the top of Caltech campus on one of the roofs of one of the buildings. And he was able to get a transit as well. So you can do this even on light polluted areas as well, which is pretty nuts. A lot of these targets are bright, 10th magnitude in V or brighter, and we have people with telescopes as small as 3.5 inches, 4.5 inches that are giving us science-grade data. So Exoplanet Watch is this collaborative effort that we have to complement existing surveys. So we're trying to be as collaborative as possible. All of our data is immediately public. We have no proprietary phase. Currently, we're updating our pipeline every 2 days, and we'll be hopefully doing that every single day very soon. And any new results we get is immediately published to our website. We also have target requests. I'll talk about one a little bit later, by professional astronomers. So they'll say, hey, we have an upcoming run on James Webb or Hubble. Can you help us observe? And we'll say yes. Also, observers are listed as co-authors. So if you observe a transit event and your data is published for the first time, we're asking those authors to include you as co-authors as well. Because if you do the work, you deserve the credit. And we're also funded for the next few years by NASA's Universe of Learning. So for the Citizen Science Project, we have both educational goals and also science goals as well. The science goals really is mostly to update those transit times and also to potentially discover new planets and confirm exoplanets as well. to monitor stellar variability. I can talk about that later at the end if anyone has a question about that. And we also have our educational goals, given we're a citizen science project, to engage and teach the public about astronomy and hopefully inspire the next generation to join astronomy or STEM fields as well. And sorry, Rob, I just saw your question about redshift. Rob is asking online, or stating in line, the redshift allows us to find planets whose orbit does not necessarily line up with the Earth, but the tilt of the exoplanet's orbit affects the redshift. How do we count for the tilt? So Ryan, or Rob, excuse me, my name. Let me go back to my radial velocity slide. So Rob is absolutely correct. In this, there's a degeneracy between the mass of the planet and the inclination of the orbit. Because if we can have an orbit like this that's planar or perpendicular to our line of sight, or parallel to our line of sight, and that could be a relatively small planet. But if I tilt that signal a little bit and put it at an angle, we're seeing less of the redshift because some of it's tilted off of our line of sight. So you can either, if there's a higher inclination, you can counteract that and still get a big signal by putting a big planet there. So there is a whole degeneracy between the inclination of the orbit of the planet and the planet's mass. And one way to break that degeneracy is to use the transit method. The transit method directly tells us the inclination of the orbit. And Steve, there is a target list for the 0.76 SRO telescope. You can actually go to the Swarthmore Transit Finder right now, and the Exoplanet Watch target list is already built in there. So I'll talk about that in a second as well. But we can also bother Ryan to add it in too. I'm picking on Ryan a lot because we play ice hockey together. So Ryan and I play ice hockey on a very nerdy science-based JPL team at Pasadena Ice Skating Center. And Ryan is one of our fastest skaters and is really great about annoying the other team, which is what we love. And he also puts up with me, so I like that too. All right, so let's pretend you tolerated my really nerdy jokes and you still want to join Exoplanet Watch. So there's two ways to get involved in this project. One is if you have your own telescope, and another is if you don't have your own telescope. So let's pretend, we're Ryan and we're using our own telescope to get observing in this program. What you do is you just go on our website, just Google NASA Exoplanet Watch, and there's a whole target page on there. And we have this really nice built-in tool. We're using the Swarthmore Transit Finder. Swarthmore Transit Finder allows you to find any transiting exoplanets anywhere in the world for your own telescope. So if you folks are calling on the line, you can actually use this tool to search for your local neighborhood as well. And then you go out and make your own observations. But if you don't have your own telescope, or let's pretend you go to the Pacific Northwest where it's all cloudy all the time, you can actually get data from us. We're very, very lucky in that the Micro Observatory, that 6-inch telescope whose data I showed you earlier, they've donated over 10 years of data to us, about 2,000 data sets. And you can go on our website right now, type in your email address, prove you're not a robot by clicking on stop signs and a little grid of images. And within a few minutes, you'll get data emailed directly to you. And then, after you get that data download, you analyze your own data. So we need your help to turn those FITS files, those images, into scientific grade data. And you can use whatever analysis code you want. A lot of people use AstroImageJ as a popular one. We also have our own in-home software called Exotic that we actually have really helpful tutorials as well. And it really simplifies the analysis of this transit data. I'll talk about Exotic in a minute, so I won't talk too much about it here. But after you analyze your data and you turn those FITS files into a transit light curve, you then upload your data to the AAVSO. That's the American Association of Variable Star Observers. They very, very kindly are letting us use their database for free. And this is great because for some reason we were trying to figure out how to get people to give us their data and contribute their data to the project. And when we were thinking about how to do this, it was very abundantly clear that JPL doesn't like random people uploading data to their servers for some reason. Go figure. So we had like a whole convoluted way of doing it with like Dropbox or email and then AVSO, I talked to them like, oh yeah, we have that already. I'm like, thank God. This has really made our lives so much easier. And thanks to them, we actually have gotten hundreds of observers. A majority of our first-time users came directly from AVSO. And those who aren't aware, the AVSO is one of the oldest observing communities in the entire world. And it was founded in the US about 120 years ago. And they actually have observations, visual observations in their database from the early 1900s, which is pretty cool. And they've been storing data for over 100 years. So it's a very natural connection as well for us. Then after you upload your data and you give it over to us, you sit back, relax, crack yourself open a beer if you're over 21, and you get published. Or you can publish your own papers using our data. You can go on our website today and download any of our data products, and publish your own paper as well. The only thing we ask in return, you cite our paper, because I'm a very petty person, and you also give us an acknowledgement to keep my bosses happy as well. Cool. So I mentioned Exotic. This is our data analysis code. Sorry, this slide is very busy. I forgot to update it with the less busy one. But Exotic, what it does is this is your complete data analysis tool for exoplanet transits. What Exotic does is it takes your raw physics files, it calibrates them by doing flats, darks, and biases. It picks out your ideal comparison star. It figures out your optimal aperture, your sky annulus size. It also fits your time series data to a statistically motivated light curve fit as well. And this works in as little as 4 minutes. So you can upload your data to Exotic, push a few buttons, and come back after you grab a soda, and you can have a science grade data set here waiting for you when you get back. This can run locally on your own computer, but we recommend people use it on the online portal. So basically you just open up a page in your browser, and right there you just push a few buttons and answer some questions, and you get your data analyzed for you. So you can actually run this completely on your smartphone if you wanted to. You don't even need a nice computer to do this, because this runs all on Google servers. Then what happens behind the scenes is we have this pipeline at JPL. It scrapes the AVSO, downloads all the data, we reprocess it, and we immediately publish it to our website. And that happens about every other day. And so far, we're really proud of what we've done so far. We just launched to the public back in January. We had some limited launches the last 2 years. We've been developing this project the last 5 or 6 years. And so far, we have over 2,500 people worldwide from, I think, every single continent except Antarctica. And this is actually an example of one of our data sets that we had. We had a big campaign, observing campaign about 2 years ago, where some folks that were using James Webb wanted us to observe this transiting exoplanet, to update its transit time. The problem is that this transit event takes over about 20 hours to observe. So it's literally impossible for any single person to observe the entire transit event. So what do? We simulated a giant worldwide telescope, and we had folks starting off in Eastern Asia, I believe that's Japan. We have folks in India, passing off to people in Eastern Europe. We have one that looks like the Canaries, maybe, and then out to the West Coast. And then some people picked it back up in Japan again. And we combined all those data sets together, and we simulated effectively a single worldwide telescope. And this is something I'm super proud of, because we've been talking about doing this for the last 10 years, and we finally did it, which is cool. And we had about 24 facilities. All of them were relatively small telescopes, less than 30 inches. A majority of them were actually 4.5-inch telescopes, who gave us really great usable data. And of course, on this one night, most of the northern hemisphere was clouded over. Of course. I remember looking at the sky maps and just seeing clouds everywhere. So we had probably another 10 to 20 to 30 other people that wanted to join, but were clouded out. So this effort shows why a distributed network of telescopes is necessary. You can help observe these longer transit events that are literally impossible for a single professional observatory to observe. In addition, we're able to basically hedge our bets on weather, because clouds always seem to come out when you want to observe all the time. I don't know how they know that. And here we were able to luckily still get the transit data. And from this, we were actually able to save the James Webb Space Telescope about 3 to 4 hours of observing time. So I just saved you all $4 million. You're welcome. Feel free to write me a bonus check if you want. I'll accept $400,000. It's a paltry sum. All right, so here's a QR code. There's our website address. The easiest way to find us, though, is just to go on the internet and search for Exoplanet Watch or NASA Exoplanet Watch, or bother Ryan, and he can tell you where to go, because sometimes Ryan does this too. So that's the best way to get in touch with us, if you are not tired of my bad jokes yet. All right, so I'll get off my soapbox right there. really quickly, as a recap, we find exoplanets using the radial velocity and the transit methods. Another method that I use personally at JPL is something called the direct imaging method. And can anyone guess what the direct imaging method does? How does it work?
Directly image it.
You got it. Astronomers are not inventive with their naming. Taking photographs of exoplanets. There you go. You're jumping the gun, but you got it exactly. We block out the sun. So if you want to take a photograph of an exoplanet, just as I alluded to earlier, it's a very difficult thing to do simply because the stars are so dang bright, to use a technical term. Yeah. So let's try to make a quick thought experiment to make things as easy as possible. Let's take a really large planet, like a Jupiter-sized planet. Let's also observe it when it's relatively young. So it just formed, it still has a lot of residual heat from when it formed due to the friction of the gas and dust as it collapsed in together. So it's glowing in the night sky. It's far away from its host star in a Jupiter-like orbit. It's also super bright. And that planet is still 1,000,000 times fainter than its host star. That's like looking for the light of a single firefly around a lighthouse off the coast of New Jersey. That's all well and good. You know, young planets are cool, I guess. I really want to find aliens. I want to find Earth-like planets down here. That Earth-like planet around that same star, though, is 10 billion times fainter than its host star. That's like looking from the light of one bioluminescent alga around that same lighthouse off the coast of New Jersey. So how do we do this? And as you perfectly predicted, we can use something to block out the light of the host star. So those of you who saw the total solar eclipse and even the partial solar eclipse, when the moon passes in front of the sun, the moon blocks out the sun's light and you can see stars around the sun. Same exact idea. You can get a little disk, move it in front of the star, block out the star's light, and then observe the planets orbiting around that star as well. This is called a chronograph. And this was actually built and first invented by astronomers about 100 years ago because astronomers wanted to observe solar transits, to actually observe solar eclipses, because they realized the science you can do. You can study the outer levels of the corona. You can actually, solar eclipses were actually one of the first ways that confirmed Einstein's theory of relativity, because they were actually able to watch the bending of the light of these stars around the sun, which is pretty incredible. So Einstein came up with this theory of relativity. The next year there was a solar eclipse, and they actually were able to confirm it that way. So this was made by impatient astronomers. Necessity is the mother of all invention, right? So you put a little disc called a chronograph, block out the star's light. You can then observe a solar eclipse, similar solar eclipse. And today, 100 years later, we're using basically the same technology, more or less, to observe exoplanets. So let me just share my sound right here. Let me turn up my volume. So here's a cool little animation about how direct imaging works.
A coronagraph is a way to see distant planets hidden by the glare of the star they orbit. The coronagraph reduces the light coming directly from the star to separate it from the light reflected by the planet. The Nancy Grace Roman Space Telescope's coronagraph doesn't block the star's light with an opaque disk, as a simple coronagraph might. Instead, it uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover, distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects distortions in the light beam. As the mirrors deform, the blobs of light slowly begin to disappear, revealing brighter planets. Further adjustment brings fainter planets into view. Advanced software processes this data, further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, the Roman Space Telescope will provide the first look at individual planets in star systems that might be similar to our own.
So we'll talk about the Roman Space Telescope and the coronagraph in a minute. That's basically how coronography and direct imaging works, right? Magic! You use really sophisticated computers to do a lot of intense post-processing. You build the coronagraph disks to block out the light as much as you can of the host star. And you also have these deformable mirrors, which are a lot like adaptive optics on large telescopes, to counteract any aberrations in the optical beam train at all in the telescope as well. And this method has been used very, very successfully over the last about 15, 20 years or so to observe exoplanets. So here's an actual real data set taken with either Gemini North or South over about 7 years. You can see that little counter on the bottom left. Here at the center of the image, that is where the host star is. And you can see that the coronagraph disk has blocked out a majority of the star's light. It's not perfect, right? You still get some light leaking around the coronagraph mask. But despite that, if you look, there's 1, 2, 3, 4 little dots of light. Those are actually exoplanets orbiting around this host star. So observing an extrasolar solar system with the planets orbiting around its star in real time over 7 years, which is just mind-blowing. And seeing something like this is what really helped inspire me to work on direct imaging as well, because it's just absolutely incredible. We're looking at a solar system out there, hundreds of light years away. So this is with ground-based telescopes. This is what's typically used to do direct imaging. Large 5-meter class telescopes are larger. Actually, the smallest telescope that I'm aware of that can do direct imaging is Palomar, actually the Hale telescope by Escondido out here. Typically, though, it's done by 6, 8, and 10-meter class telescopes, Keck's, Gemini's, Magellan's. But as I'll talk a little bit later, we're going to be doing this for the first time in space using the Nancy Grace Roman Space Telescope. Okay, so now what? So, we've discovered over 5,000 exoplanets. And we know that exoplanets are ubiquitous. There are at least as many planets as there are stars in the sky. But how do we take that next step from planet discovery to planet characterization? How do we determine, for example, does a planet have an atmosphere? And if a planet does have an atmosphere, what molecules are present in that atmosphere? Does it have water? Does it have methane? Does it have carbon dioxide? Does it have the molecules necessary to support life? And if so, does that planet have life on its surface? Just because a planet could support life doesn't guarantee that life is formed on the surface of that planet. So this brings us to step 2 on determine if a planet can support life. One way we sort of do this as a quick first order estimate is we use something called the habitable zone. This is also called the Goldilocks zone. And this is the zone where liquid water is at the right temperature where it's liquid on the surface of a planet. The planet's not too hot like Mercury or Venus. It's not too cold like Mars. Water exists, at least not in Southern California, but other places in the world. I've heard rumors of water out there. And the reason we care so much about water is because when we look at Earth, all life requires liquid water to survive. So where we find water, we might also find life. This is why NASA is so interested in following the water on Mars. This is why we're so interested in following water elsewhere in our solar system, as well as exoplanets. So at the bottom, there's a top-down view of our solar system. There's the Sun, Mercury, and Venus are a little bit too close to the campfire. They get boiled away. Mars is a little bit too far away. It's too cold. But Earth is at just the right distance from the Sun where we can have liquid water on our surface and therefore potentially life as well. This is all well and good. This kind of helps us whittle down the current sample of 5,000 exoplanets to the 10, 20, 30 that we want to study in more detail. But how do we make the next step and say definitively whether that planet has water on its surface or in its atmosphere or not? And one way we do that is by using this thing called Beer's law. This is actually an extremely powerful law that astronomers use, and myself as well, to characterize the atmospheres of these exoplanets. And I found this really cool definition online on how Beer's law works. And that's defined as studying for a test or doing homework while beer is involved, making difficult classes such as physical chemistry more bearable. That's a great one. I did that a lot in grad school myself. But here's the real Beer's law. It's a little overwhelming, but basically what it says is let's do a thought experiment. Let's put and take a light bulb on one side, and then between us and the light bulb, we have like a chamber of gas, like water vapor in that chamber. If we were to look at that light bulb on the other side of that chamber of water vapor, we would expect that light bulb to be a little bit dimmer because some of the light is absorbed and scattered by the water molecules, just like the sunlight is obscured by clouds. And that amount of scattering or absorption adheres to this relatively simple physical law right here. So basically, what this enables us to do is we can observe what a light source or an object does look like, compare it to what it should look like, and then from that, we can actually figure out what's causing that absorption or scattering of the light. And this is really, really helpful because the nearest exoplanet to us is over 3 light years away, about 1,000 to 10,000 years to travel there with today's technology. And as much as I love frequent flyer miles, I also like watching Netflix. So this is really nice. So let's look at some examples. Let's say we're an astronomer, we're observing a yellow star. We would expect that star to look what color?
Yellow.
Yellow. Just making sure you're all still awake. Good. That yellow star emits yellow light. We see it as yellow. But if we put a nebula or a dust and gas cloud between us and that yellow star, the nebula will absorb some of that star's light and cause the light to look reddened. So we'll actually see that yellow star as red. And then if we observe what the star does look like, it does look red. And we compare it to what it should look like, it should look yellow, like a solar type star. We can actually determine the composition of this gas and dust cloud simply by using Beer's law. And we can figure out that there's molecules like hydrogen and helium in that gas cloud. We can do the same thing for exoplanets. If we're observing an exoplanet, a lot of them have very hot or warm cores, just like our own Earth. And if we're looking at like a Jupiter-like planet, it has a big gaseous envelope. That heat and light at the core is emitted, and it starts off very hot. But as it goes through more and lower layers of the atmosphere that are increasingly cooler than the center of the star, that yellow light that was very hot comes out as red. And then astronomers, that nerdy on the other end, they can use Beer's law and determine that that planet has methane in its atmosphere. We can do the same thing in our own solar system. We have Jupiter, for example. The sun emits some yellow light. It hits the surface of Jupiter, and you see that light reddened because Jupiter, as astronomers can tell you, has clouds on its surface. So we can actually characterize the composition of targets just by looking how they interact with the light of their host star. So Beer's law allows us to characterize an exoplanet's composition by observing how it emits, absorbs, and reflects light. Again, super helpful because we don't have to travel there. So let's really quickly look at some data. Here's some actual data taken by a large ground-based telescope, I believe one of the Gemini telescopes, maybe in Hawaii or Chile. And we have 7 exoplanets here, ranging from top to bottom. And they go from cool planets on the bottom to relatively hotter planets up top. And along this axis, we've taken the light emitted by these exoplanets. We passed it through a prism and spread out the light into its rainbow of colors. It's exactly like that Pink Floyd album cover where you have the white light coming in through the triangle and out comes the rainbow. Same thing happens here. We have light coming into the system and we spread it out to see how the light varies as a function of wavelength. And this enables us to actually study the composition of a planet. At these 3 band passes right here, this is where water most strongly absorbs and emits light. So if I see a bump and wiggle at any of these 3 wavelengths, I can infer that there's water in that planet's atmosphere. Similarly, if I see a bump and wiggle at these wavelengths, I can infer that there's methane in that planet's atmosphere. And right here is where carbon monoxide absorbs and emits. So just by looking at the signatures of light that's being absorbed by these planets and emitted by these planets, we can figure out the composition of their atmosphere. And some of you in the audience might have been noticing these lovely gaps in the data. Anyone guess what that's from? I think I heard the right answer twice. Nice. That is from telluric absorption from the Earth. That's where our own stupid Earth gets in the way. Stupid Earth has things like carbon dioxide and oxygen and water and methane. That's the same stuff I want to observe in these exoplanets. And the stupid Earth gets in the way of its own atmosphere and blocks us from observing those wavelengths of light from the ground. So what's the solution?
From space.
Go up into space or hop on the top of a mountain or take a ride on an airplane? Exactly. And this is why space telescopes are so crucial. Not only do they absorb the scintillation effects of the Earth's atmosphere, they're also above a lot of the absorption of the Earth's atmosphere as well. And they enable us to observe wavelengths of light that we cannot observe from the ground. And that's one of the reasons we're so excited about James Webb. It's been doing transformative science with almost every single observation is like a Nature or a Science article. It's incredible nuts. James Webb, for context, the Hubble Space Telescope is about a 2.4 meter diameter telescope. James Webb is 6 to 8 meters, I forget exactly which. It was actually built out here in SoCal at Northrop Grumman. It's pretty cool. I got to see it in person. This thing was so giant that it actually had to fold in on itself like origami to fit in the nose cone fairing of its rocket. The purple thing on the bottom, that's a solar shield. That's the size of a tennis court. So a truly massive space telescope. And from that, we've been getting really incredible data. Here's spectroscopy. So just like those bumps and wiggles plots I showed earlier, James Webb is doing this with transiting exoplanets. And it's been looking at water molecules like water is in here. There's some sodium absorption, carbon monoxide, carbon dioxide, methane. So James Webb is actively observing and making tons of observations that we previously only could look at a small portion of. Here in gray, these are the wavelengths that the Hubble Space Telescope typically observed at. So you can see right here how much more wavelength space we can cover. At these Hubble wavelengths here in gray, that was where water absorption happens. So we were mostly only finding or have the ability to look for water. But James Webb, with this increased wavelength spread, coverage enables us to look for a lot more molecules, and by merit of its giant telescope aperture, can do it at high precision as well. So it's pretty awesome what James Webb has been able to do in it just launched a year ago in like a few days from now, which is incredible. A mission I work on at JPL is the Roman Space Telescope. This is actually named after Nancy Grace Roman. She was NASA's first chief astronomer ever. And she's sometimes called the mother of the Hubble Space Telescope because she was actually one of the main proponents of getting Hubble launched. So in her honor, they've named the Roman Space Telescope after her. This is a Hubble-sized telescope, also 2.5 meters, but it has 100 times the field of view. So Roman can do Hubble-quality science 100 to 1,000 times faster than Hubble ever could. And on board, it has an instrument that's being built right now at JPL, which we just finished the first round of testing a week or so ago, to do direct imaging. And this will be launching no later than May of 2027. Excuse me. So as I mentioned earlier, currently we're limited to using large ground-based telescopes and observing planets that are far from their host star that are big and bright. What Roman does is it enables us to look for smaller planets closer into their host star that are also temperate, cooler planets as well. And that's necessary because with future missions, we want to observe small Earth-like planets in Earth-like orbits around sun-like stars. But in order to get from where we are up here to where we want to be here on the bottom, we need Roman CGI, the coronagraph, as a stepping stone to demonstrate the technology and the techniques and the methods and the data analysis and the hardware to demonstrate that all for the first time on sky, so you can then build that into the next generation telescopes that'll be launching in the 2030s. And those are explicitly being designed right now to look at Earth-like planets and potentially detect life. So you might be asking, Rob, all right, you sold me on space-based telescopes. I guess Ryan can do some science once in a while from his driveway if he wants to. He's not playing ice hockey or whatever. Why even bother with the grounds, because space-based telescopes are amazing. You're not limited by Earth absorption. You're minimally impacted by sunlight. But there's very few precious resources. There's one Hubble. There's one James Webb. And everyone is trying to get on those telescopes in the entire field of thousands of astronomers. Ground-based telescopes, though, they're numerous. You have your own telescope up in a mountain, this astronomy club. A lot of astronomy clubs have their own professional-grade observatories. Or people can buy, for about $1,200, a 6-inch slush-drawn, an equatorial mount, and a pretty cheap digital camera and you can observe a transiting exoplanet tonight. You know, the Earth's atmosphere gets in the way, sure. And there's some annoying systematic errors to deal with. But ground-based telescopes really are important and still have a niche in astronomy. And this is why we're commissioning an instrument right now at Palomar called NESI, the New Mexico Exoplanet Spectroscopic Survey Instrument. Here's the 200-inch Hale telescope, big dome, commissioned in the 1940s. And it's the same exact telescope that was built by Hale et al. Back in the 40s. This was the world's largest telescope for about 50 years. And the only thing that's really different today is there's some fancier computers and there's our instrument on the back. Otherwise, we're using this, you know, historic, about 80-year-old telescope, which is pretty incredible.
Where, can you point out where you're going to be?
Yeah, so our instrument is currently in this room right here in a little lab. And yeah, I'll show you in a sec. I'll have some photos, actually. So perfect timing. So here's actually a picture of Nessie. No, that's a mythical sea creature. So here's an actual picture of Nessie, our instrument, in one of the labs at Palomar, right here. And Nessie, what it does is at the prime focus of the telescope. So it takes the place of the secondary mirror of the Schmidt-Cassegrain alignment. So the light comes in, hits the primary mirror, reflects up. Normally it would hit a secondary mirror and go to the instrument bay at the Cassegrain focus on the bottom. Nessie, to preserve its wide field of view, is at the prime focus. They flip out the secondary mirror, light comes in, hits the primary, and then hits Nessie. So here's Nessie being lifted up in the air during its first lift check. Here's my boss at JPL, Mark, ignoring me as usual. That's fine. Here's Michelle Creech-Ekman. She's the principal investigator, and her team of students helped actually designed and built this instrument. I love her very appropriate Nessie t-shirt on. And here we're doing the first ever lift test. So we're actually taking the instrument off the floor of the observatory and hoisting it 110 feet up in the air over this very historic 200-inch mirror. Right now, as it gets lifted up in the sky, I'm hoping our insurance has started. And hopefully we have not destroyed a historic site. But spoiler alert, we got it up there safely. It fit. Here's a picture of Nessie at the prime focus cage at the top of Palomar. Here's we're doing some testing to make sure it survived the lift test and it works. Here's Mark smiling. He's actually laughing at me because if you remember, I'm terribly afraid of heights. But I'm the JPL commissioning lead for Nessie, which means I get to go 110 feet up in the air above the telescope to work on it. But I get really cool photos like this, so it kind of works out in the end. So it kind of looks like a spacecraft, which is pretty cool. And we've already gotten some really great data with Nessie. So if you can compare this to the data that I showed much earlier, it's amazing what a 5-meter, 200-inch telescope can do. I did the estimate on this. We're getting roughly within a factor of 2 of the precision of the Hubble Space Telescope, just using a ground-based telescope in Escondido. All right, getting towards the end here. So we finally made it to our third step of our 3-step method, finding life. Just because a planet could have life doesn't mean it does. And just because it does doesn't mean it's easy to find. So how do we find life? Let's do a thought experiment. Let's launch a telescope out into orbit, like Voyager 1 or 2 or the Pioneers. And while it's cruising out to Jupiter, Saturn, Uranus, or Neptune, we can have it point back at the Earth and look for the telltale bumps and wiggles, the spectral signatures that indicate that life exists on the surface of that planet. We could look, for example, for evidence of oxygen that's output by plant life here on the surface of the Earth. We could look for liquid water, either in our atmosphere or in our oceans. Alternatively, we can actually even look directly for signs of biological activity, like cow farts, right? We can look for methane and other products that are sort of a byproduct of life. But we have to rule out all other explanations. And this is really difficult because we're currently finding tons of water. It's one of the most abundant molecules in the entire universe, and it's proving to be everywhere in exoplanet atmospheres. We're finding methane as well. But you have to figure out how, in concert, we need that molecules to exist in the planet's atmosphere to tell us definitively that life exists in the surface. And that's actually extremely difficult to do. And lots of astronomers are trying to figure out what signals do you look for that tell you that there's potentially life on the surface of that planet? Or we can do the next cool thing and send out messages to aliens, because people love talking to aliens too, right? Voyager 1 and 2 just built down the hill at JPL, launched in 1977. They had these golden records on board here, and these records had recordings of life on Earth, videos and pictures. They also had sound as well. And on these golden record covers, they actually have instructions on teaching aliens on how to read the phonograph, how to display the information properly and read it out, how to display it on your handy-dandy TV screen. And then in case if you liked Earth enough and wanted to invade it, here's where you can find us, using some pulsars nearby too. So yeah, this is a great little, come here and invade us sort of map here. SETI, in addition, sent out a signal to M13, the Hercules Globular Cluster. They used Arecibo, which used to be the world's largest telescope, and then used to be the world's second largest telescope, and now it's kind of dead, unfortunately. But they looked at M13 and they said, hey, tons of stars. Where there's tons of stars, there's probably tons of planets and probably tons of life. So they wrote this message out to aliens. So can anyone guess what the red thing is? Shout it out.
Humans.
Humans, good. Anyone guess what the white stuff is up top? Yeah, so the white stuff up top is about talking about how we can know how to count and also elements as well in atoms. Here, anyone guess what this blue thing is with the white down the middle? I'll give you a big hint, this double helix thing. Yeah. DNA, exactly. I think someone already said this out loud, but what's the yellow stuff? Right here? That's the solar system, exactly. There's the sun, there's Mercury, Venus, Earth elevated, because that's where we're from, Mars, Jupiter, Saturn, Uranus, Neptune, and guys, this was the 60s, 70s, when they didn't know any better, they had Pluto on this map. No, boo, boo. This is scientifically inaccurate, boo. And then down here in purple.
See, it won't be the first time we pull the wool over their eyes.
There you go. So it actually worked out, because now we won't be invaded, hopefully. And this purple thing at the bottom is actually a top-down view of part of Arecibo. So this message to aliens is saying, hey, we're humans. We think we're kind of smart. We know about numbers and molecules and atoms. We know about DNA. We know how to count. We sent the signal using Arecibo. Here's where we live. Please don't invade us, sort of a thing, basically. So, yeah. The fun fact about M13, though, is that since these stars are so densely packed, it's actually really hard for planets to form, because the gravitational tug of the stars tend to kick planets out of orbit and cause them to be rogue planets or free-floating planets. It actually wasn't until about 4 or 5 years ago that the first planet was ever discovered in the globular cluster. So that's probably a good thing, right? Less invasions, maybe, hopefully. Who knows? All right, so the question is, we're wrapping up now, finally, is where are we now? So unfortunately, despite what the History Channel and Ancient Aliens has told you, we have yet to make any conclusive detection of extraterrestrial life. And the question is, why haven't we found life yet? There are as many planets as there are stars in the sky. Planets are everywhere. Stands to reason we should have found alien life or heard something by now. Well, maybe our technology isn't good enough. It wasn't until the mid-90s that we were able to discover exoplanets. And I would argue that was the invention of the CCD camera array that helped us make this discovery. Because before it was on glass plates, which is a pain. And this really made it a lot easier to collect a lot of data at high precision. Or maybe we just haven't found them yet. Maybe they've been talking to us from this patch of sky and we've been staring over at this patch of sky instead. Jill Tarter, she's actually a SETI scientist who is the inspiration for Carl Sagan's book and movie Contact. She had a great analogy. If we took the entire observable universe and shrunk it down into the size of the Earth's oceans, we really only explored the equivalent of 1 glass of water's worth. So while we think there's a lot, that we know a lot about the galaxy and the universe, we still have a lot more left to discover and explore. Or maybe we are all just alone, to leave you on a very down note. Maybe life is very infrequent. Maybe it's very, very special. Maybe it only exists here on Earth. Personally, I think that alien life has to be out there. We haven't discovered it yet. And I don't think we've discovered it yet. So I'll get lots of people who come up to me after talks and say, Rob, I know you have a security clearance. I know you can't tell us about aliens. I know you're hiding the truth from us. And one of the biggest people that do this to me all the time is my brother-in-law. Here's an actual picture of my brother-in-law. And it is his modus operandi to get me very drunk at family gatherings, which I appreciate. That's nice. So he'll ply me with really good whiskey. And then once I've had a few, he'll be like, all right, tell me about the aliens, Rob. It's okay. And he never believes me. It's great. I love Ryan. But we haven't found them yet. And it's really in our best interest if we were to discover alien life to everyone know. Because one of the reasons I'm giving this talk to you today is to, you're an astronomy club, you know about the benefit of NASA, other than keeping me and Ryan employed, which we appreciate. It's also, giving these talks helps, to get public excited and keep on paying their taxes. So thank you for paying your taxes. So wrapping up now, here's sort of a look back and also a look forward to what we can expect on exoplanet missions. So thanks to all the great foundation that's been laid and continues to be done by ground-based telescopes, both big and small, we have tons of data from Hubble and Spitzer and Kepler. TESS has discovered and expected to discover 10,000 exoplanets. James Webb is, with every new observation, is making impactful, groundbreaking, transformative science. The Nancy Grace Roman Space Telescope will continue that. That's the next NASA flagship mission that's launching in just over 4 years from now. Good Lord. And that will be looking at directly imaging exoplanets. And on the European side, we have Ariel upcoming at the end of this decade that'll look at 1,000 planets. But it doesn't stop there. The next generation of space telescopes that are being devised right now, they're being called the Habitable Worlds Observatory. This is a mission that'll be launching in the 2030s and 2040s. And this is a telescope and observatory that's explicitly being designed right now by folks typically at JPL and also Goddard on the East Coast to discover planets that are Earth-like, around solar-like stars that are temperate, that could also have life on their surface. So perhaps within the next 10 to 20 years, we'll finally be able to answer that question, are we alone in the universe? And with that, I want to chug some water and happy to take any questions that you have. Thanks for having me. And I'll make sure to also repeat the questions for folks online. And thank you for the nice words, Rob. Appreciate it. Rob said, great job, Rob. You were not totally horrendously horrible. Great. Just kidding. He sent me something very nice. Yeah, go ahead.
So how much consensus is there among exoplanet scientists on what a life signature might look like?
So the question for the folks online is there any consensus about what a life signature looks like for exoplanets? And that's a great question. I think if you ask me, I think that's a question that's very much open still and something that people are currently studying right now. Some folks think it's a concert of water and carbon dioxide and carbon monoxide and methane, and the abundances or the amounts of those molecules can tell us if it's formed by biotic signatures or formed naturally, abiotically, without life as well. But I would argue it's still, up for debate. And if we were to observe these planets and see those signatures, we still, I would argue, we don't have that slam dunk signature. Like say, if you see this signature, we know 100% that life is out there. Likely what will happen is we'll see a bunch of molecules, and then scientists will say, well, in order to get this amount of carbon dioxide or this amount of oxygen, it requires something other than volcanism or plate tectonics to cause it, or even and you might need like plant life or biological life as well. But they'll say like, we think within 75% or 50% chance that there might be life on this planet. So that's what will likely come out of it. So yeah, we don't know really. And you're welcome, Steve. Thanks for the nice comments as well. Elaine, any other questions? Yeah, here in the front, go.
There's a lot of double stars out there.
Yep.
Does that affect what you're doing? I mean, you're looking at the planets on single stars?
Thank you for that great segue, Gil. So I brought some posters. Ooh, sorry folks online, you can't pick any of these up. But if you want to search on the internet, I also have them for free here. This is actually a planet that we discovered called Kepler 16b. And it's actually just like Tatooine, you have a single planet orbiting around a binary star system. So hopefully there's an angsty Luke Skywalker on there. I can't talk about that right now. Yeah, so we
Question
actually
online?
did this with Hubble a few years ago as well, Kepler 16b. So these posters up here, you're all welcome to grab them. I have some travel posters. I have some Roman chronograph stickers and NASA meatball stickers as well. But yeah, we're finding planets in binary and I think also a triple star system as well. And typically, they'll either orbit around both or they'll orbit around one. Typically, yeah.
Question online?
Oh, one second. What was that question more
How
time?
many Jupiter-like exoplanets have been discovered?
So the question for folks online is how many Jupiter-like planets have been discovered? So Jupiter-sized planets, a majority of them are, because they're so much easier to find. But true Jupiter analogs that are at Jupiter orbits and at Jupiter temperatures, only a small handful of those planets. Typically, what we're doing right now is we're discovering planets called hot Jupiters. Again, a very inventive name. But basically, they're Jupiter-sized planets in fast orbits around their star. So that means, and they're going on their star super fast, like on the order of, some of them go around their star every 45 to 90 minutes. Typically about 2 to 3 days. And we're able to observe these really quickly because it's easy to see a transit event a couple times, even a week. They're also Jupiter-sized planets, so it's a big signal. But they're very close to their host star and very, very likely that they're not habitable. But then going for a more temperate, true Jupiter analog, let's see, Jupiter orbits around the sun, was it every 2 to 5 years or so? Does anyone remember how quickly Jupiter orbits around the sun? 11 years, even worse. Great. So in order to see a transit or to see multiple transits, you have to wait 11 years between those observations. So that makes it a lot harder. Even with the Earth, right? If you have an alien trying to observe Earth, if they wanted to take multiple observations to stack their data together to increase their signal to noise, they have to wait 365 days for the next event to occur. So it's not very efficient, unfortunately. Yeah. I think we had a question online as well. You want to unmute yourself?
Yeah. I had a question. This is Jan. If we wanted to detect oxygen, what would it take to do that?
If we wanted to detect oxygen, what would it take to do that?
In an exoplanet atmosphere.
Yeah, so I think actually...
Where on the spectrum do we see that?
That is a great question, and I honestly forget. But let's see if it's in this James Webb data. Yeah, so we need a spectrograph, exactly, or at least the photometric passbands to get us to the light that we're looking for. I don't remember offhand, honestly, what molecular oxygen absorbs that, and I think James Webb probably doesn't have the precision to do that, but hopefully the next generation of instruments will. So I don't know the exact answer for your question. Sorry about that. All right.
Will the
Yeah.
artificial intelligence accelerate the search for exoplanets and life on exoplanets?
Yeah, and scientists have been using AI and machine learning really for the last 5 to 10 years to discover exoplanets. So that's extremely helpful on missions like TESS. So TESS is observing almost every single star in the sky at a cadence of at least, over a month. And it slews around the entire sky in about 2 years. So there's tons of images out there, and it's literally impossible for a single user to do that. So they do this in 2 ways. One, they have an automated pipeline that uses machine learning to look for a transit signal and to say this is likely a transit event, like a planet. Also, there's a citizen science project where they'll put the data from TESS online, and you can help look for any signals the pipeline has missed. And actually, citizen scientists have helped discover about 5 to 10 TESS planets because it missed the pipeline, but a human eye is still needed in the system to make sure we don't miss the signal. So that's another way you can get involved through citizen science as well, is that effort is called Planet Hunters, or Planet Hunters TESS. But yes.
Are you all actually incorporated this kind of intelligence in the present satellite and telescopes and all?
Yeah, people have. It's typically the machine learning is not on the spacecraft systems themselves. It'll be on the running on the data when it's downlinked to Earth. So TESS will take all the data, it'll shuttle it down through the radio telescopes to Earth, and then people will run their pipeline here on faster computers. Because, supercomputers are very, very power intensive, and there's very limited power margins that we can put on these telescopes as well. Yeah, great question, thanks. Any other questions from online or in person? I think in the back first.
Yeah, the transit method like Kepler used.
Yeah.
What's the approximate width in degrees before
that be typical of that star is tilted and you won't see any transits?
Yeah, typically, so for folks online, it was the question about the inclination of the orbit and what inclinations can we tolerate before the planet passes too far above or below the star due to its misalignment. I think it's roughly about 75 degrees to 80 degrees.
75.
It depends on also the distance of the planet to the star. So the closer the planet, the more tolerance you have. The farther away the planet, the less tolerance you have as well.
You could presume planets that don't show transits should also have planets, and I mean stars that don't show transits, and that they're just at the wrong angle to us.
Exactly. Yes, this is something I forgot to mention, and you're absolutely right. There stands to reason there's a ton of planets that were missing because they never transit their host star. So I think it's roughly half of all transits were missing because they just don't happen. They don't have that geometry. Yeah.
I think it'd be a lot more than that, but
That's the number I remember looking up a few years ago, but it might be different now for sure. But yeah, that's big. Backing that estimation of what we're missing is a big part of how we're able to estimate how many planets there are in the entire sky, for sure. Is not only discovering what we do see, estimating what we don't see, and then figuring out that there's as many stars, planets, as there are stars in the sky. Yeah, great question. I think you were next.
And then on all those future telescopes that are going up in the sky, is there any thought of having one where people go with them and work them out there?
If you want to volunteer and go up to the telescope and spend 20, 30 years up in orbit, be my guest.
Well, they could, come and go like they do with or something.
So for the question of folks online are they ever thinking about taking people up with the telescopes and observatories? They've actually done that on the International Space Station. So they actually used to have a relatively small telescope on the ISS, and they actually think they have one in the Chinese space station as well. The reason why you can't do that with these next generation missions is they're going to a point called L2, or the Lagrange point. This is an orbit. There's the sun, there's the Earth, and it's just on the other side of the Earth, past the orbit of the moon. And at that position, the orbit and the gravity is relatively stable. So you can send something out there and it can just sort of sit out there forever, more or less. That takes, James Webb took over a month to get out there. So I would not recommend that trip. If you want to volunteer?
Sure, I'm ready to go.
Yeah.
Where's the test?
TESS is it's actually in a very elliptic orbit. So technically TESS is an Earth-centric orbit, and it goes out almost to the orbit of the moon, I believe, and then does this really quick pass that's a lot closer to the Earth, and that's when it does its data downlink, is when TESS does that. But then it spends a majority of its orbit out farther away from Earth, farther away from the sunshine and the thermal heating issues as well. The Hubble Space Telescope, by comparison, is in a Earth-centric orbit, and it is not a geocentric orbit, so it's orbiting around the Earth every 90 minutes. And as such, 45 minutes of that orbit it's in sunlight, the other 45 minutes it's in darkness, so we only have an efficiency or duty cycle Hubble that's roughly 50%. So whenever we're planning observations, we have to take that into account, that half of the time we can't use Hubble because the sun's in the way. Stupid sun. Maybe we can just turn it off. That would be helpful to do. But that's why a lot of large telescopes like James Webb and the Roman Space Telescope are going out to L2. A lot more of the sky is more accessible. About half the sky any given one time, take into account solar exclusion angles, and it's just a lot more thermally stable, so you get a lot better data quality as well. Great question. Any other questions from online or in person? We have another one here in person.
I read that the extrasolar search is now focusing on sub-Neptune sized planets, and why is that?
So the question for folks online is why our search is more focusing on sub-Neptune planets, and that's simply because up until the advent of Kepler and TESS that have launched in the last 5 or 10 years, we've been mostly sensitive to finding Jupiter-sized planets. So we're always trying to push the boundary. The ultimate goal is to get down to an Earth. So looking for sub-Neptunes is the next step. So we've been finding lots of hot Jupiters because they're the most easy to find, the easiest to find. However, hot Jupiters are not a typical planet type. So we're now trying to find more sub-Neptunes and then Earth-like planets as well. Yeah. So it's just about trying to march our way down to getting higher and higher precision observations.
And you mentioned planet around one of the stars of globulars, which I never heard of, which is interesting. Recently we had a lecture on M15. You know, maybe if not, many globulars have black holes in them.
So probably not a good place to live then, to stay in a globular cluster.
How many of you probably, most of you are old enough to have maybe seen Nightfall, the movie? Is it Asimov? Isaac Asimov? Nightfall? No? How many? Let me see a hand who've seen Nightfall. Oh my gosh. It's about a planet within the globular cluster. And only one day out of 10 years or so, they get to see stars outside. If you're living in the globular cluster, you have so much stars, you can't see the night sky. But one day out of about 10 years or so, that sky is black. Yeah, so Nightfall is an interesting movie. I don't know if they've shown it, right? It's certainly in the books.
Yeah, and there's actually some planets that are what's called tidally locked to their host star. So just like with our own moon, which is tidally locked to our own Earth, one side of the moon always faces the Earth. Some of these planets are also tidally locked with their own star as well. So one side of the planet will always face the star. That means one side is always in perpetual night, one side is always in perpetual day. And that heat contrast sets up a huge temperature contrast between the dark side and the light side of the planet, which actually causes really intense winds, some that break the speed of sound as they transfer heat from the hot side to the cold side of the planet, which is pretty nuts. But perhaps maybe life could live on the Terminator, where you have that division of light and dark as well. But maybe not. It sounds like not a great place to live. I can barely tolerate the Santa Ana winds, so that would not be fun. Any final questions from either in the room or in online as well?
This thing in Puerto Rico, it just fell apart one day or something?
Yeah, it basically, it's a giant telescope. It's so big it's actually in a valley between mountains, and it just got older over time, and they didn't have the money to upkeep it. And there was a hurricane or two that also came by, and some of these cables broke, and then the secondary cone fell into the dish and shattered it. And so it's no longer around, unfortunately. Yeah. Ryan.
Regarding people observing exoplanets at home, transits at home, you mentioned one of the benefits that you're able to get out of it is the mean transit time. Are there other things that you're able to resolve from those at-home observations?
Yeah, so a big one, there's actually two big ones. So one is also measuring the impact of stellar variability. So whenever we're making transit observations, so the question, sorry, for folks in line was, is there any additional science cases that people can do other than updating the transit times with their telescope observations? And the answer is yes. A big thing that we're starting to have to really worry about right now is the impact of stellar variability. And that's because when we're making these transit observations, everything is relative to the host star. So if we observe a transit today around an active star, and we come back in a week, and that star has changed its activity, maybe it has more flares, maybe it has more spots, just like our own sun goes through periods of activity and inactivity, that can actually impact the transit signal that you observe, because it's always relative to the host star. And up until now, before the launch of James Webb, we've been able to sweep that underneath the rug. It's been a minimal impact mostly. James Webb, though, it's so stupidly big and precise and sensitive, we have to take into account now. So figuring out the impact of stellar variability is something that small telescopes are actually incredibly adept at doing. And by figuring out the variability using small scopes, we can hopefully help correct for that in the James Webb data as well. So that's another part. So let's say, for example, TESS is observing the entire sky. It's not only discovering new planets, TESS is also updating the ephemerides or the timings of these targets. Let me get TESS up here. There's TESS. So let's say TESS does all the timing updates we need. We're still going to need people on the ground observing these targets to monitor their host stars to quantify the stellar variability, even if TESS does all the timing measurements. Because TESS, while it observes the entire sky, it can't do it simultaneously. So your target might be happening over here, but TESS might be staring at this point of the sky, and that's just your tough luck. Another thing we can do with these transit observations is we can actually look for and infer the existence of extra planets in the system as well. Because what will happen, So we have a star and we have two planets. The inner planet will orbit around the star. The outer planet's gravitational tug will sort of tug the inner planet back and forth. So one orbit, the planet's transit will come a little early. And when the planet tugs it, the outer planet tugs the inner one, the transit next time will come a little late. And we can look at those variations of the time, and we can actually help discover additional planets that are in the system. And there's not really a lot of groups that are doing this over a large baseline. So this is something that's unique in the world that TESS can't do, because TESS can only look at a field maybe once for a month and then not come back for another 2 years in some fields. Great question, Ryan. Thanks. Any final questions? No? Well, thank you again, folks. Oh, yeah, sorry, Ryan. Ryan's keeping you all here. It's Ryan's fault.
The benefits of citizen science and at-home telescopes. Is there any particular benefit, maybe signal to noise ratio or something, of say a 30-inch class telescope?
Like a 0.7 meter class telescope, maybe from Southern California at the San Gabriel Mountains, maybe. Yeah, with your 0.7 inch telescope, you should be able to observe super Earths, which is pretty awesome. So I've done the math a while ago. So actually Exoplanet Watch has a bunch of telescopes at Wrightwood, just northeast of here. We have a 0.4, a 0.6, and 7 6-inch telescopes. And I did the math on the 6.6 meter, and we can actually get that down to super Earth-sized planets. So we're trying to have the smaller telescopes, like the 4 to the 6-inch class telescopes, to observe the hot Jupiters, the big planets. But then something like your telescope can help us observe smaller planets, but also planets around dimmer stars as well. And that's crucial for James Webb planning as well. So yes, please help, please. No worries. All right, is that the final question, I think? Cool. Thank you, everyone, for having me. Really appreciate it. And yeah, thanks again.